Hey everybody. So this is your notes for day 4. And this might be a little bit of a long video, so you'll probably want to pause at some point. But I'm going to try and do the whole thing in one go. To kind of recap where we've been so far, day 1 we talked about the proton-proton fusion chain that happens in the sun. I mentioned before that your test has one FRQ question on it, and it's specifically on doing that proton-proton chain. So you want to make sure that you know how to do WebAssign A1 come test day. We also talked about the birth of stars and protostars on the first day. Second day, we went on to high mass stars, elements forming between helium and iron, and then elements forming above iron. Day 3 was low mass stars, their lives, helium to carbon fusion at the end, and then planetary nebula. So today's focus is on stellar evolution, and that is how stars evolve through their life cycles. So if we take a look here, we have high mass stars, low mass stars, and these are the notes we got to get through. There's 7 stages to these cycles. So we'll start with a high mass star, and both high mass and low mass start with the same idea of a protostar, in which there's a gas cloud that collapses under gravity. The next thing, the second phase, is once you get that gas cloud to contract, it heats up and you get fusion. Now, for high mass stars, they're going to be called blue MS stars or blue main sequence stars. They do a little bit of a different fusion cycle as opposed to the proton proton chain. They take 4 hydrogens and fuse it into 1 helium. This is known as the CNO cycle. You don't need to know how the CNO cycle works for the test. Just know that it's a different cycle that's using high mass stars. You'll also notice that these stars are blue. So, why are they blue? It has to do with the fact that they're hotter and their peak emission, where it comes out to be. So, what this graph is trying to show you is the y-axis is the emissions of radiation coming from the star, and then the x-axis is the color spectrum. You have infrared, then Roy G. Biv, and ultraviolet, and it goes on into X-ray and gamma. And sure enough, stars emit all the way from radio to gamma. And whether they're blue, yellow, red, doesn't matter. So these high mass stars are hotter. And in general, what we can say is that as you move this way, you get more energy. So more energy, therefore more heat, and it's going to glow bluish violet, and that's where it's going to peak. Our sun, for example, actually happens to peak right around green. Our sun appears very white because it's a very healthy mix of red, green, and blue. And if you combine those 3 colors of light, you get white. Our sun appears yellow to us on the planet because a lot of this blue gets filtered out through our nitrogen-based atmosphere, leaving reds and greens, thus appearing yellow. Some of the lowest mass stars would end up peaking in the infrared or near red spectrum, so they might see something like a peak emission like so. And these peak emissions determine the color of the star, and the color of the star is an indicator to astronomers how much heat and energy there is in it. Now, what's going to happen is the hydrogen is going to run out, and the star is going to become what we call a red supergiant. So the hydrogen is exhausted and the core shrinks. Now, as the core is shrinking, you're getting more gravitational energy being converted into heat. And then now a hydrogen shell will begin to reignite and conduct fusion. That hydrogen shell is surrounding an inert helium core. Now, because that hydrogen shell burning begins to occur, that throws off a tremendous amount of energy, and that pushes the outer layers of the star outwards, causing it to expand. And that's how it becomes a red supergiant. Eventually, that hydrogen burning will cease, and helium burning will begin in the core. Now you have a helium burning supergiant. The helium fusion begins in the core, and it's forging it into carbon. It's 3 heliums that fuse into carbon. At this point, the core expands, and then this slows the hydrogen shell's burning rate, and the outer layers begin to shrink. So your star started off as blue, it expanded, became red. Now it's begun to shrink. Once that helium core fuses into carbon, you're going to end up having a multiple shell burning star. So the helium runs out, the carbon sinks to the middle, and this process of it expands again because the helium and hydrogen shells are burning, but the core is inert. So pushing the outer layers outwards, becoming big. And then once the core begins to ignite fusion, it shrinks again, expands, shrinks, expands, shrinks. So that kind of, it begins a cycle through 3, 4, and 5, repeating these shell burning, core burning, shell burning, core burning. Ultimately, the core is going to become iron, and iron is the graveyard for nuclear energy. You can't get energy out of iron. And that's where it's going to go. Stage 6, supernova. Iron can't provide any fusion energy, so it builds in the core until the degeneracy pressure can't handle it anymore and the core collapses. When the core collapses, a shockwave sends out the supernova. The final remains of this star is a neutron star or a black hole, and that's what the core collapses into, one of those two things. To kind of show you the chain, regardless of what kind of star, they all start as protostars in a gas cloud. Our massive star, remember, it's got to be at least 8 times the mass of the sun, burns blue, becomes a red supergiant towards the end of its life. This is where it expands, contracts, goes supernova. What we call it is a type 2 supernova. You can see there's type 1 supernovas. We're not getting into that detail in this class. The supernova remnant is a giant gas cloud, also known as a stellar nursery, where new stars will form. In the event that the star was less than 40 times the mass of the sun, it will become a neutron star. If it was more than 40 times the mass of the sun, it will become a black hole. And then more things can continue to happen with those remnants afterwards, but we won't be considering ourselves in this class. The low mass stars, so this is something like our sun. Again, protostar, all stars start as a protostar in a gas cloud. Gravity contracts it. That gravitational potential energy gets converted into heat, and you get fusion. You get a yellow or red main sequence star. Now, in the core of the low mass star, that's the proton-proton chain that we talked about on day 1. That's going to be on your FRQ for this test. This process is going to occur for billions of years. To put it in perspective, the supermassive stars only last for about 5 to 6 million with an M years. These low mass stars last anywhere between 5 and 100 billion with a B years. Now, and that's just as the main sequence. Then you have the death phase of the giant, because it will do a red giant phase as well. It won't be a red supergiant like the high mass stars are, but it will still turn into a red giant. Now, similar to the high mass star, after the hydrogen's exhausted, the core shrinks, and you get hydrogen shell burning again, just like on the other high mass stars. That's going to push the outer layers outwards, causing it to expand to a red giant. It will contract once helium fusion ignites in the core, causing the core to expand and slowing down the hydrogen shell burning. And then you get a double shell burning red giant. Depending on the star, our sun won't get beyond this. It will never fuse carbon, but it will fuse helium. So it will go to a double shell burning red giant, burning again, hydrogen in one shell, helium in the other. It expands due to the extra nuclear fusion reactions. Now, some of these can get to the point where they can fuse carbon, but that's really about it. They're not going to get beyond that. So really, the main sequence phase for these stars is very long as opposed to the high mass star. But then the death process is very similar, where expands, contracts, expands, contracts, expands, contracts. In the end, when the core collapses because it can't handle the pressure due to gravity anymore, there isn't as much gravity in the low mass star, so you just get a planetary nebula, and the core actually remains. It doesn't turn into a neutron star or a black hole. Now, the core is hot, but there is no fusion. And so the outer layers get blown away in a recoil effect as the core collapses, called a planetary nebula, which may go on to form other stars. The core becomes what's called a white dwarf, and the white dwarf is primarily carbon, might be oxygen if your star was able to do carbon fusion, but mostly carbon and oxygen. Now, it glows because it's hot, not because there's fusion, and it will slowly cool over time. To show you visually, here's your low mass stars, less than 8 times the mass of the sun. Um, they can get as small as about 9 to 10% the mass of the sun. Those ones are the ones that live for about 100 billion years in the main sequence phase before going red giant. Now, we're not going to worry about this chain here because we're not studying that. You get to the red giant, they expand, contract, and then you get your planetary nebula, a white dwarf. A black dwarf is the idea that eventually this white dwarf will cool down enough where it's no longer giving off light and it'll just be a ball of carbon and oxygen. At that point, we will call it a black dwarf. You'll see in here, if you're curious, the last one's called a brown dwarf. That's less than 8% the mass of the sun. A brown dwarf is a very, very large sphere. It would dwarf something like the planet Jupiter, but it wasn't quite big enough to get hot enough and begin hydrogen fusion. So it's effectively a failed star. That about concludes it. These notes will be posted on Canvas for you, and that's kind of a wrap for today.